everyone. As you have seen the title, we are gonna be discussing about FanOut for delay. Like I have heard this uh, now only. Like I haven't heard this before. This is like I know what is FanOut. I have some basic idea. Like if you have a logic gate, some logic gate, it can be described in a way such that uh, how many gates that this logic gate can try effectively. Uh, Effectively in the sense each and every gate has its own gate cap, right? It has to charge these gate capacitances. For that, we need some driving strength for this logic gate. So, fan-out is a term that describes how many gates, or you can say how much load that it can bear in such a way that it can effectively, properly charge these capacitances, load capacitances. And this is like this can be modeled or mathematically written with respect to the input gate gap. So every, let's take an inverter. Any logic gate has some gate gap, right? So any logic gate will have a gate capacitance. So we need to charge this first. So there will be some other gates connected to this output. We can model that as load cap. So let's say this is input gate cap. So fan out is nothing but output cap capacitance by input capacitance. So this is fan out. So I have mentioned that FO4 delay, right? So we are talking about delays. So why should we even discuss about delays? Mm, let's say ideally, let's say there is an inverter and I'll give input, I'll get some output. Let me plot those input and outputs. Let's say I have given 1 at this time. It will be really good if I get immediate response at the output at T1 itself. Life will be easy. I will be having a processor. If I just give some inputs within no time, like within no time, it will give some output. Everything will be super fast. Can do infinite number of operation within no time. So actually that doesn't happen in real time. If you give if you give some input, let's say this one, it will take some time for the output to be uh, like it's an inverter, right? For the inverter, it will take some time, the output takes some time to get reflected according to the input. So this time is the delay. So as you all know, any RC circuit, let's say I have given some voltage here, some resistance. So any RC circuit will have some delay, right? And we measure that delay quantity with RC. It's a time constant. If you don't know what is time constant, uh, if you derive voltage expression, let's say this is the V out. So voltage expression for this capacitor in terms of resistance and this voltage input, let's say this is input. So V in 1 minus e power minus time, and this is time constant tau. So in VLSI industry, not VLSI industry, basically in logic gates, we consider VDD by 2 as the switching threshold. Switching threshold voltage. So what is this switching threshold voltage? It's just simple, like if you could observe here, output is transitioning from one state to the other, and there is an instant change, like it's discontinuous. And again, in real time, this is not what's really happening. Reality is it maintains to be one, and here there is a change, right? So here it starts to change its value. So this is the transition, not this ideal discontinuous transition. So this is the ideal one, and here let's say this is VDD and this is 0, and here somewhere here it is VDD by 2. So this is my switching threshold point. You can easily understand from this graph that at this point right side will be 0 and left side will be considered as logic 1 high, right? So this is the switching threshold. So I need VDD by 2. So if you could deduce this, do some calculation, you'll get, let me do it. V out is VDD by 2. This is VDD 1 minus T by tau. So tau is nothing but the RC. We'll discuss about this later. It depends on the transistor, because we are talking about transistors, right? Especially CMOS. So it depends on RC, and VDD gets cancelled. I have 1 by 2 minus 1 minus E minus T by tau. So this is minus 1 by 2, minus minus cancels. This is e power minus T by tau. Natural logarithm of 1 by 2, so we'll get minus T by tau. So this is minus 0.69 and minus t by tau. Thus we get time as tau 0.69. This is the time at which output voltage is VDD by 2, that is switching threshold voltage. So this is 0.69 is a constant and tau is RC. So 0.69 RC. So clear, right? These are the basics. So if I get into the transistors, you take any MOSFET, let's say for N diffusion we'll use green. This is N plus diffusion and this is P substrate and this is the gate. Assume this as a gate. I'm not accurately drawing everything according to the layout diagrams rules and all. So this can be anything. We can short this to ground, this to the output. So let's say this is output. So this entire thing can be represented with the simple diagram. Let's say this is the ground and this is the VG gate and this is the Vout output, these two. So and there is another terminal, that is bulk voltage at the bulk substrate body, you can say anything, and this is actually connected to source itself, and we can just connect this to source ground as well, and there is a direction, right? So that direction can be easily identified by considering that this is a P substrate and we have a N channel, right? In order to get this transistor working, there has to be an N channel form, like electrons, a channel form with the electrons. So this can be modeled as P type and N type. P type, N type, diode direction is like this. So we can draw an arrow like this. So this is gate, arrow is pointing towards the gate and the arrow will be like this. And again, so what I'm trying to say is, we talked about RC, right? So where is this capacitance coming and where is this resistance coming? So whenever you try to give some input, I mentioned that there is some gate capacitance. We have to charge the gate first. Then this transistor turns on or off, either way, and it will charge the output or discharge the output depending on the transistor, what kind of transistor we are turning on or turning off, depends. So we first need to charge the gate and discharge the gate, either way. Let us consider that we have NMOS and at present it is zero gate voltage and we are trying to make it VDD. So it's transitioning from 0 to VDD. So there has to be some electrons to be aligned in a line between source and drain, that is called channel. It has to be formed, right? If you could carefully observe that this metal and this channel acts as a capacitor, this and this. In between there is some insulator. that is actually SiO2. So we have some, we can say that as CG, gate capacitance. We can say NMOS. For an NMOS, it's the gate capacitance. And again, if you observe, this is P substrate and this is N plus diffusion. And at normal, like at room temperature, we can observe a diffusion, right? There will be some diffusion current where electrons will jump from N diffusion to P substrate and makes ions, right? Negative ions. And this will be positive. Thus, we have some capacitance here as well. This one, and let me use different color. This one. So this is a different capacitance, and let me emphasize this insulator as well. What is insulator? Insulator is nothing but the semiconductor material properties. Like semiconductor itself isn't a good conductor nor a good insulator. It's in between, right? So it can act like a semiconductor. So actually we can consider semiconductor material itself as a insulator, and there is a capacitance formed here. So this is called as diffusion, like you can say diffusion cap because it is formed because of the diffusion. But the thing is, we can even call this as drain cap because you may say that uh, let's say there is a capacitance here and there will be some capacitance here as well, right? This is also capacitance. Then this is also a capacitance, right? So this is what? This is diffusion cap, but on the source side, and this is diffusion cap on the drain side. Here what happens is it is connected to source and this is connected to bulb, which is again grounded. So there is no potential difference between these 2 points and this capacitance. There is no charge on this like capacitor. So we ignore this. Usually we ignore source capacitance when the terminals of the body and source are shorted. Okay, so this will be ignored and we only consider this diffusion, drain diffusion, right? So we'll consider it as the drain capacitance. So what do we have? We have this drain cap and this gate cap. So usually in any technology, whether it be 16 nanometer, 22 nanometer, 180, 90, 130, whatever, we usually consider CG drain cap to the gate cap equal to 1, approximately 1, not exactly 1, approximately 1, and we denote this ratio as gamma. So this is just a we did this for mathematical ease of operations. Like it will come handy. This is called as calm, and it is uh, process dependent because we have to diffuse this n plus region and gate in such a way. Gate in the sense gate ka SiO2, that insulation gate thickness depends on the process, right? Whatever the foundry people are doing, it depends on that. So gate cap depends on the thickness, and it is depends on the process, like what kind of how controlled process is undertaken. So this diffusion and this cap has to be like almost equal to one, their ratio. So this is done, capacitor is done, and we need resistance. Sorry. So what is resistance? Resistance uh, is just a opposition of flow of current, right? So how do we measure this? So it's actually a hectic job for us to extract the resistance out of these transistors, because it's not really uh, that direct. That, let's say if you take a conductor, will have some length, it has some weight, you can calculate the area. It has some, like, depending on the material, let's say copper has some resistivity, it has some resistivity. So with that we can calculate the resistance. But semiconductor is entirely different. It depends on the several aspects. So what we do is several aspects in the sense, um, let's say it depends on the kind of p substrate we have used and kind of in diffusion that has taken place, and kind of resistance also depends on the temperature as well. That is entirely different thing, like we need to consider that as well. And it also depends on the length of the channel, width of the channel. Width is the major significant, it plays the significant role in the resistance. If you increase the width, resistance will reduce, we all know that. So everything will be considered, mobility, everything will be considered, and the designers, like, or else RC extraction people, usually backend people do this. RC will be extracted, like resistance will be extracted according to the technology and process that has been undertaken. So resistance will be extracted, and this is a hectic job. We need to do a lot of analysis and a lot of mathematical operations has to be taken place. It's a hectic job. At the end we'll get the RC. C is also depends on the diffusion and gate thickness and all, right? So RC extraction is really important, and it's a difficult job which can be slightly that hard work can be reduced by using some mathematical probabilistic methodologies. We can arrive at some approximate values, that is RC extraction, sorry. So why do we discuss all this? See, if I have resistance and capacitance, I can calculate the delay of particular transistor, let's say either PMOS or NMOS, right? If I have R and C, I can calculate the delay. So consider a inverter. This is VDD, this is ground, and there is some capacitance here. We'll discuss what it is. And there is some capacitance here, and it is visible that these are connected to gates, and this will be gate capacitance, right? Gate capacitance. And if you know that PMOS is connected to VDD, then it's obviously a source, right? And NMOS is connected to ground. This is also source for the NMOS. So this is drain for both PMOS and NMOS. As we discussed, there will be some drain capacitance. So this is the drain capacitance, the inverter, and this is the gate cap of inverter. So now we need to extract the resistance and these capacitances, right? And also remember that this drain, C drain over C gate, is approximately 1. गामा से रिप्रेजेंट करते हैं ना, so we represent that with gamma, so approximately 1. Okay, so here this RC extraction is something that can be used while designing, while uh, calculating the delays, while doing the ST analysis. We'll send these values to the standard libraries like standard cells. There will be some standard cells, right? Those timing analysis tool, let's say from Synopsys, there is prime time will have some standard cells. Within that there will be some predefined delay values for a standard cell. Those are obtained using these extracted RC values. With these extracted RC values, we'll find out the delays of the standard cells. Those will be used by the tools like prime time. Clear? So we are not extracting any R here. We are not trying to find out the exact finite value of the resistance that is felt by, like observed in the PMOS or NMOS. We're trying to like standardize the resistance. Like there is PMOS, there is NMOS. Both the transistors will have some resistance. This is Rn, this is Rp, PMOS and NMOS. So as I said, this resistance depends on the kind of substrate we have used and kind of process that has been taken care, like that has been carried out. It depends on the diffusion strengthness, like whether it is strongly diffused or a lot of aspects. So this resistance also depends on this channel and all those things. So at the end, after several analysis, we found out that resistance of PMOS is actually approximately around 2 times the resistance of NMOS. This is obtained from the current equation. Uh, we can deduce from this current equation PMOS minus, you will get to know that it depends on the mobility of PMOS to the mobility of NMOS. NMOS will have a lot of I would say, let's say in, if you can see here, in NMOS there is N channel, right? Like channel is formed using channel formed by electrons, and PMOS channel is formed by holes, right? We all know that. So mobility of holes is actually half the actually this relation is wrong. Mobility of holes is one half of the mobility of electrons. We can say that, yeah, mobility of holes, uh, other way, mobility of electrons is double the mobility of holes. I'm just confused. Yeah, mobility of electrons is double the mobility of holes. So in this way we can find out that, we can say, how did you find this resistance? Simple, like IP, drain current of PMOS, is proportional to mobility of PMOS, and from Ohm's law, current is inversely proportional to resistance. So thus we can say that if mobility of electrons is double the holes, then resistance of PMOS has to be double the resistance of NMOS, right? So why do we even care about this? See, at the end we need delay, right? There is some transition in the input, let's say 0 to 1, and the output will have some transition. It takes some time, and let's say there is another transition from one logic to the other, a bit different state, and there will be a transition here as well. If you see, whenever for an inverter, if the output is going from 0 to 1, that in the sense the load cap is charging up, then it has to be connected to VDD by PMOS, right? And during this transition, it will uh, it will observe, it will feel a resistance of RP, correct? At the same time, when the inverter is transitioning from 1 to 0, when it is discharging, it is connected to ground via NMOS, and it will feel a resistance of RM. Then, and delay depends on RC, right? C is constant for this transition time from low to high, and this transition high to low. Drain wouldn't change, right? Drain तो हमेशा वही है. Drain is always constant. Drain capacitance wouldn't change in these two transitions. R is the culprit that changes. In one transition it is RP, and in one transition it is RN. So if you want to generalize and say that delay of an inverter is some quantity, then you have to take care of this RP and RN, because for rise time and fall time the delays will be different, but I need some finite quantity. It has to be same for low to high and high to low. So for that we need to make sure that RP and RN are equal, resistance are equal. For that, what can we do such that resistance of PMOS and NMOS will be same? It's actually, I have discussed about this. Resistance depends on several aspects. In that, width can be used, which can be altered in such a way these to get equal. We can do that. We have a relation that Rp is 2 times the Rn. So why don't we just double the size of Rp so that its resistance decreases by 2, right? By a factor of 2. So I'll increase the width of Wp twice the Wn. So twice the Wn will be Wp. So now this width of PMOS will be 2 and width of NMOS will be 1. So now this is the standard inverter, you can say that, because we have considered everything that contributes to delay. Tau is RC. We have taken care about the capacitance. Capacitance is just a constant. It doesn't matter. It doesn't uh, it doesn't have any effect on rise time or fall time. It is constant for both the cases. Resistance is the one that changes. So we have sized it accordingly. So if I give input, I'll get output uh, without any consideration of kind of transition it is having. It will have both low to high and high to low as same delay approximately. It's not like we have 2:1 ratio. I'll get same delay for low to and high to low. It's not like that. We approximately say that they are equal. So that's it. So now on we can find out the capacitance, because for NMOS it is 1, right? Width of NMOS is 1. So this drain cap of NMOS will be, let's say, 1C. Drain cap of PMOS as 2C, because with this double, as you know, this is the width. Lunch, this is the width. So as you increase the width, capacitance will obviously increase. So this is 2C and this is 1C. Thus we have a output, we can say drain cap of inverter is 3C. And whether it be whether the capacitor is charging or discharging, resistance will always be R. And we'll consider this entire inverter standard cell as a minimalistic logic gate, because we are not using any complex, like more than one PMOS isn't used here. Only one PMOS is used, only and one NMOS is used. So this is a minimalistic logic gate that we can build using this PMOS and NMOS, CMOS basically. So this is our min, this is VDD, and this is the diffusion cap, like drain cap. I'll get confused with C drain. So This is 3C. So what is the time constant for this? Tau will be 3RC. And again, it's same for the discharging as well. This will be turned off, and this is the cap. This is the drain cap, which is 3C. It doesn't change, it's constant. And this actually it's actually Rn, but we have sized the NMOS and PMOS in such a way that it will be equal to Rmin. Rmin is nothing but the basic, like we can consider it as resistance of NMOS as well. Okay, so this is Rmin. So this Rmin of PMOS has to be 2R, and Rmin of NMOS to be R. Actually, switch the terms now. You can say that, as we already know, Rmin is 2R and this Rmin is R. So the minimum resistance of the pull down network in a minimalistic inverter standard cell is R, and for PMOS, Rmin is 2R. So whenever I talk about one exercise, like this is the standard, you can consider this as a standard cell. Okay, this standard cell PMOS has a resistance of 2R and NMOS has a resistance of R. That's fixed. So here time constant is same, 3RC. So both discharging and charging time constants are equal, approximately equal. So now finally we can write an expression for delay. Delay is equal to what? It has to be proportional to resistance, that is Rmin, and the drain capacitance, right? This is delay. And what we are actually calculating is we want to reach the threshold voltage, switching threshold voltage, right? Which is VDD by 2. So we can multiply this by 0.69. From now we can consider that as K, constant. So Rmin, C drain is nothing but 3C. So K3RC. So this delay can be, from now on we'll consider it as TP, propagation delay of inverter, right? So this is the inverter's delay. So until now we haven't discussed anything about fan out, right? So we'll come to that from now. So we have characterized the inverter, we have extracted the resistance, and capacitance is calculated. From these two we have calculated the delay of the inverter. Fine, let's say what if I what if I load this inverter with some load capacitance, and there is this gate cap every time, gate cap of inverter. I haven't discussed it that, right? Actually, it's really simple. This gate cap is actually 3C as well, because we have discussed that diffusion to the gate cap ratio is almost 1. we have considered diffusion as C, then gate cap, unit gate cap will also be C. So we can say that 3C. Why? Because PMOS is contributing 2C and NMOS is contributing 1C. So 3C. So now if I load this inverter with a capacitor with the capacitance CL, what would be the delay? So delay will be resistance that comes every time, and the drain cap plus load cap. So load capacitor is an extra thing that we have added now. C drain plus C load. So 1 second. Okay, let's continue. Sorry for the interruption. Hmm, where did I stop? Yeah, what if I load this inverter with a capacitor? So this is the equation. Life is happy. There is this one, only one extra load cap. Include this in the expression, we'll get the delay. Yeah, that's correct. That's so straightforward. There's nothing complicated in that. So yeah, okay, it's fine. Just leave it here itself. Now let's say you have around mm, let's say there is an inverter and there is a gate cap of, let's say, 1 coulomb. Okay, and there is a load cap of 100 coulombs. I'm saying coulombs, I'm saying this capacitor C, and I started saying coulomb, sorry. Farad, 1 farad and 100 farad. So actually in the ICs with for these logic gates there won't be this much of capacitances. Those will be in some picofarad order, something like that. For simplicity, let's consider 100 farad and 1 farad. So the thing is, delay will be k times resistance drain cap. Drain cap is nothing but the, let's say CG is 1F, right? 1F in the sense 3C is equal to 1F, correct? So drain cap is 1F and load cap is 100 farad. So I'll get 101 KR delay, correct? So if you try to calculate this, let's say R is around, let's say, 1 ohm. I'm making it really simple. And K is also, it's 0.69, right? Let's ignore this K value for now. I'm just calculating RC. So ignore this. So this will be 101 RC. What is RC? Like ohm, farad. RC will yield what? That's a constant. We don't have to think much about it. I'll think about it later. So we have 101 time delay, correct? So it takes this much of time. Let's say mm, there is a load of 10 farad and 1 farad gate input cap. So tau will be a resistance which is 1 ohm, same for the inverter. So 1 ohm, that will be 10 plus 1, 11, right? Tau will be 11. So you can see that it's evident that delay depends a lot on load cap. And if this is really high, tau will be really high. And one more thing, that let's not discuss about that. Let's say that tau is very high if the load cap is really high. Okay, so with this abstraction, I have actually have a code. this will come in handy later on. Yeah. So what I'm trying to say is driving this 100 farad by this single inverter takes huge time. Delay will be huge. So we have to do something so that the delay will reduce, right? Delay will reduce. So what is this driving the load cap? It takes a lot of time. What is this electrically? What the concept? What is the internal working of the inverter? Let's discuss about that. This is the PMOS and NMOS. These are connected, and this is VDD, and this is ground, and this is the load cap. So let's say it is charging up. So there is some RP resistance, which is actually 2 times the RL, and this is equal to Rmin, correct? So there is a capacitor, load cap, it is charging up by VDD. So if you see electrically, this RC time constant can be reduced if the R is very low, like resistance is low. If you reduce the resistance, delay will reduce. And to reduce the resistance, I need to decrease the width of the device. So width of the device has to be increased, right? Sorry, I got. Okay, width has to be increased. So if width is increasing, then capacitor will increase, right? In order to reduce the resistance, I increase the width. That increases the capacitance. So in a way, these two are like fighting each other. So, but eventually, what you do is, if you consider the expression tau R C diffusion, like drain cap plus load, if I size that by W, if I increase the PMOS and NMOS by W, resistance will reduce by W, correct? And drain cap will increase by W. But there is no effect on load. Load is something different. That's completely different. It's not part of the inverter. It's coming from other logic gates. In reality, it comes from the other logic gates. So if you take this into this capacitor wala, you'll get drain cap CL by W. So actually, if you size the inverter, delay actually reduces, correct? If you size the inverter, delay reduces. This is evident in this expression. So life is happy now. Let's just take an inverter. Even if you load this by 100 farad, I'll size my inverter in such a way the resistance is really low and the current flowing through this PMOS or NMOS is really high, and thus this discharge of 100 farad and charging will eventually, the time will eventually reduce by W amount. But the only thing is this gate cap is also increasing now. If you can see carefully, this gate capacitance offered by PMOS and NMOS for a minimalistic inverter is 3C. If I size this by W, this will become 3WC. What's there in it? If you uh, consider the overall picture of an IC, you don't have only a single inverter. You have billions of gates, millions of gates. So this inverter must be fed from other logic gates, right? It could be AND gate, it could be OR gate, it could be NOR gate, it could be anything. So it is being fed by other logic gates. So in a way, we are increasing the load cap of this previous stage logic gates. So we are increasing the load cap. So again, we need to size these gates, and sizing of these gates results in the increase of gate cap of this logic gates, and this triggers the need of sizing the logic blocks that are here. So it's a hierarchy thing. So there has to be some methodology where there has to be some approach where we can charge and discharge this big elephant by some logic without, like, not only this inverter. Usually we have only one inverter. It is driving this 100 farad elephant with little 3C cap, which is 1 farad. So we have to introduce some logic here such that this load, like, there is some load on this inverter, right? Back then there is 100 farad load. It has to put on some effort to drive this, to charge this capacitor or to discharge this capacitor. Now I'm including some other logic gates to take care of this big giant. You might say that this is counterintuitive because uh, inclusion of these logic gates will increase the propagation delay, right? If I give one input, and if I want to reflect that input at this output node, there will be some increased propagation delay, right? Because each gate that we are including in this cloud will contribute some delay. We add on to this delay, inverter delay, there will be some other delay as well, that cloud logic gates delay. So aren't we in a way increasing the delay of this operation? This is the operation. Charging this 100 farad is the operation, and it is being carried out by single inverter. It takes some t1 time. By including this cloud of logic gates, aren't we increasing it by adding some tau delay for that? That's the beauty that we are going to be discussing now. Actually, if you place some logic gates in between the output of inverter and this giant 100 farad cap, it, it can be anything. Like, this is really big, CL is really big, and if you add some logic block within this cloud, your delay, propagation delay, will reduce. We'll see how and why. In this process, we'll find out there will be some terminologies. Those are efforts. What kind of effort you are putting in There will be some two, three terminologies. We'll discuss about that. So this is the thing, and we get to know that this cloud will contain only specific gates, specific logic gates, and we'll discuss why only that gate. Okay, so I'm saying that if we include some logic gates in this, the delay of charging or discharging this capacitor will reduce. So what are those gates? Is it a XOR gate, NAND gate, AND gate, or a NOT gate? We don't know, we'll see. So that's the thing. And here I would like to introduce that fan out definition, that fan out is nothing but output load capacitance that a logic gate is driving to the input gate capacitance of that logic gate is the fan out of a logic gate. It just tells about the uh, uh, what is the ratio of output cap to the input cap, that is fan out. Is it a fan out? Actually, this is not fan out. You have to think twice or thrice what I'm saying. I'm not a expert in this subject. This is actually not a fan out. This is called some effort. We'll discuss about it. Some effort we call effort that is imposed on the logic gate. It is a effort. It is not fan out. Fan out is just a what we can say. Fan out is something that we have. I think I have told you about. Okay, fan out is something that how many gates, or you can say gate in the sense it has some capacitance, right? So how much capacitance, question mark, how much capacitance that an inverter can drive effectively in the sense, let's say there is a gate, some gate, logic gate, it has some capacitance. So in order to have a proper what we say, proper input, whether it be 1 or 0, 0 in the sense it has to be grounded, or there will be some noise margin. We could say it as VIL. It has to be less than VIL. So then it can be considered as 0. And for 1 it is VDD, or it should be greater than VIH. Correct? Uh, it should be greater than VIH. Then it can be considered as logic high. So for capacitor to have a minimum VIH or maximum VIL, this driving gate has to give that uh, current actually. So it has to drive this capacitor. We don't have only one gate, right? There are several gates. So several capacitances. These are in parallel. This will sum up to some big capacitor. So this is the fan out. So how much uh, output gate capacitance that it can drive is the fan out. And usually you can add inverters. You can say that it can drive these many inverters, something like that. That is fan out. Fan out 4 we'll discuss. The 4 is a magical number. 4 is a magical number. We'll discuss about it. So now how this uh, cloud is reducing the delay. Cloud is reducing the delay. How and what kind of cloud it is, what kind of logic gates it has. So let me consider NOT gate with some gate cap, and there is a cloud, right? And this is the big elephant load cap. So what you do is, uh, from now on, approximate everything. Like if I say something that this inverter is minimalistic one, like standard one, there is no sizing to it. The PMOS is twice the width of NMOS, 2:1. So this is the standard one. If I say something like that, you should for some time let's obey with me, please. So this is the minimalistic inverter. Thus we have CG as 3C. C is the you can say drain cap gate cap ratio gamma approximately equal to 1. This one is just 1C, that capacitance. Okay, so this is 3C, and this is some big giant load capacitance, which is very big. So for simplicity, let us consider chain of NOT gates. I don't know, there are n number of NOT gates. I don't know how many NOT gates, chain of NOT gates are there. So I'll draw this again. This is the NOT gate, which is the first one, minimalistic wala, NOT, 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 and this goes on. And there is the last nth NOT gate. This is the nth NOT gate. People might say that it has been sized to n. No, it's the nth NOT gate. This is n minus 1 NOT gate. So this cap is I can say Cn minus 1. So this has to be C1, this C2, this one is C3, this one is C4, Cn minus 1, and this is actually Cn. Cn is Cl, load cap. And this is the minimalistic inverter's gate cap, input gate cap. Let's consider it as CG inverter, which is actually 3C. So both heavy away. I did nothing. I'm just trying to find out the cloud of logic gates, which would reduce the delay. Delay तो कम होगा ही होगा. Delay will reduce. We'll find out what are these logic gates, and we'll get to know that why this delay is reducing. So chain of inverters with some capacitance. So delay will be what for an inverter? For an inverter with diffusion cap with some CG inverter, delay will be RC, KRC diffusion, and let's say there is a load CL plus CL. So this is the delay, but there is an entire chain of inverters, right? So how would you calculate the delay, propagation delay? And basically one more thing, I have mentioned it earlier as well. We'll discuss this about later. So 1 second. Okay, so yeah, there is uh, we don't have a single inverter, we have a chain of inverters, right? So I need to consider all the propagation delays of each and every inverter. So every inverter's propagation delay contribution has to be summed up, and thus we have the total delay. So you can say that you can write it as propagation delay of first inverter, second, um, third one, and so on. Propagation delay of n minus 1, propagation delay of nth gate. So this is the total time constant. So if I start adding up everything, so k is common for everything, like every gate k is common and r is common, right? So I can pull these two out, and for first inverter, that diffusion cap is C1, so I can write C1. Sorry, C1 is actually load, right? I'm sorry. Okay, C1, wait, C1 is the load cap. And what is the diffusion cap? Diffusion cap depends on the sizing, right? So I haven't mentioned that these all chain of inverters are minimalistic. Only the first gate is minimalistic of size 1. It hasn't been reduced by any factor or increased by any factor. So it's just a basic standard inverter, and I don't know about this. So we can uh, we can say that diffusion of this inverter is C diffusion of inverter. This is the basic one. Okay, and this one, uh, this inverter. So for this inverter, diffusion is CD inverter and the load is C1. I wrote those. This is for first inverter and this is for second inverter. Second inverter sizing, I don't know. Let's say x2, and this, okay, x2, right? So x2 CD inverter, correct? So this is the standard one, CD inverter. It has been factored by, like, it has been sized up by x2. So I multiplied x2. Load is load depends on the next gate sizing. So this is x3. So actually C1 is actually x2, right? I can write it as x2. X2 CD inverter. Let us assume, uh, actually what I'm trying to say is, let us assume CD inverter as 1. Later on we can write it as 3C. Let us assume it as 1 for simplicity. Okay, CD diffusion cap of inverter is 1. 1 in the sense, we'll multiply this entire thing by 3C later on, or we can just write it now itself. Okay, 3C. So x2 multiplied by C diffusion inverter, it has been already taken out as a common for everything. Since chain of inverters, there are no other logic gates, there are only inverters. So x2 is the diffusion cap of this one, and load will be x3, right? So x2 plus x3 and so on. This will be second gate is x2, so nth gate will be xn, and this will be xn minus 1. So diffusion gap will be xn minus 1 plus xn plus xn plus cl, correct? So this is the diffusion, like this is the delay. So this is the delay including chain of inverters. So yeah, it's evident that it has like time delay, like RC constant has immensely increased, like it's so significant. We'll see again. So if I let's just isolate this standard cell aside, this first one, I mean, uh, so 3CKR, first one will be uh, x2, right? Okay, this will be 1 plus x2. I have isolated the first inverter and I'm writing for the other gates. 3CKR R x2 plus x3. Actually isolate everything. 3CKR, that remains to be same, right? That doesn't make any sense. Okay. Okay, here there is a beautiful relation. Like I'm trying to, eventually what I do is I'll find out the number of chain of inverters that has to be added in the cloud so that the delay will be minimum. So to do that, I need to differentiate the time constant with respect to some variable so that it equates to 0. Thus, I can find out this unknown variable value such that the delay will be minimum. So in this process, I'll do some mathematical manipulations here. So if you observe this first gate is having x2 and this second gate is having x2 and x3 and so on, right? And this is xn minus 1 xn cl. So if you recap once again, that gamma that I have mentioned, gamma is nothing but diffusion cap to the input gate cap, right? This is almost equal. Ratio comes out to be 1. That in the sense diffusion cap and gate cap are almost equal. So what we can infer from this is I can write whatever so far I have written, I can write that in terms of like this is the first inverter, right? So this is actually 1, right? This we don't care about this. This is x2. X2 is nothing but I considered it as diffusion cap of second inverter. So I can write that as, consider that as input gate cap of x2, right? Input gate cap of x2. So from now on, I can consider this as x2, which is gate cap, and x3 is the load cap. Okay, and here x3 is gate cap of third inverter, and x4 is load cap, and so on. And here as well, this is x2, which is load cap, and this is 1, which is nothing but the gate cap, right? So gate cap of first inverter. So this will be x of n minus 1 gate cap plus x of n load cap plus x of n gate cap plus CL. It's just the load cap. So I have mentioned about a term called fan out. Fan out is nothing but the output cap to the input cap. Load cap to the gate cap, input gate cap. So let's say this first gate overall capacitance, you can say that it has a C1, let's say C2, C3, Cn minus 1, Cn. So here within this, if you carefully observe, there is load and gate input, load input gate, load input gate, load input gate. If I just what do we say, if I just take the ratio, uh, this is f1 is nothing but the output cap of first uh, first inverter to the input cap of first inverter, and this is f2 same output cap of C2, input cap of C1, and so on, right? So if I multiply everything, f1, f2, f3, f4, and so on, fn minus 1, fn, this turns out to be, if I write that, uh, it turns out to be first inverter load cap is x2 and input cap is 1 multiplied by second inverter load cap is x3 input cap is x2 third inverter is x4 load cap input cap is x3, such that it goes on. N minus 1 gate load cap is xn, input is xn minus 1. This is actually CL load cap, CL by xn. So this is the beauty. Fan out of each and every gate chain of inverters, if I multiply the each and every fan out of every gate, these will cancel out this x4 and x4, x3, x3, x2, x2. The remaining, uh, the last one, let's say this is, if I multiply everything and say it as, let it be, if I multiply everything and the result is load cap by first inverter input gate cap, that is nothing but CG inverter, right? Correct. So this is what, if I multiply all the fan outs of each and every gate, it comes out to be load cap by first inverter or first gate input gate cap, right? So what can we do with this? Let's see. So what will be the expression? Mm, mm. Yeah, so this is a relationship, right? What we eventually want is this is tau, this is multiplied by some k, r, some 3c, right? R. So this has to be, delay has to be very minimal. So this is very minimum value. It has to be minimal. So I'll differentiate tau with respect to some variable so that it will be 0. Like that differentiated equation is 0 such that we can get some valuable insights. Uh, 1 second. Yeah. So we'll differentiate with some variable equated to 0. We'll get some valuable insights, right? What do we really want from this entire expression? It's just the, like, there are two things. One is I want to find out the cloud. For now I assume it has inverters, so let's say number of inverters. I want to know number of inverters, and I want to know about the capacitances, like sizes, x1, x2, x3, x4. I want to know about the sizes. One is number of inverters and one is sizes of each and every inverter. So if I consider one of the variable, either of this, let's consider capacitances. Take this as a variable and differentiate the tau and equate it to 0. You'll get some valuable insights about the capacitors, like sizing of each and every stage. So let's see that. So let's say if you take, if you consider some, let's say, let me draw this again: inverter, 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 some n number of inverters and n number of, this is the load cap, this is the xn, xn minus 1, this is minimalistic standard one, x1, x2, x3, this is some xj in between somewhere. So there is a input gate cap cg input. So this is clear, right? So I am trying to find out the sizing of this jth inverter. I'll take this as a variable. I'll differentiate tau, equate it to 0, this xj. I'll take this as a variable, differentiate tau, equate it to 0. I'll get some valuable insights about jth inverter capacitance sizing, right? So what is the equation? Like this is the equation, right? In this equation, if you observe, xj is somewhere in the middle. Okay, xj minus 1. So xj is somewhere in the middle, and these are other variables: xn, x3, x4, x2, x1. These are other variables. So if I differentiate this entire equation with respect to xj, I only get these terms, the terms which are having xj. Other terms will be 0, right? So Having that clarity, we can uh, move forward that this differentiation will yield a K3CR will remain same, and I'll have, let's say this is xj, and this is the previous gate. This is xj minus 1. This is the next gate. This is uh, what do we say, xj plus 1. So what is the load cap here? This is xj, and what is this? Xj plus 1, and this is xj minus 1. So if I could carefully observe, I need fan out of this because input gate cap is xj and output is xj plus 1. Okay, and I need this gate cap as like this gate as well, because this gate's load is xj, right? So I need capacitor values, capacitor terms of these two gates, jth gate and the previous gate. So I could write it as xj by xj minus 1. This is electrical fan out. Why am I writing like this? You may ask this now. So the thing is, where is this? Yeah, actually the capacitor terms are something like this: x3 input gate cap, load cap added together, plus x2 plus x3. So are you writing that electrical fan out as a as in a time constant expression? So it's basically that you have extracted, see, you did one thing, you extracted 3C, right? Correct? You extracted 3C. So that is okay. So everything has to be multiplied by 3C, that's okay. I got stuck. Wait a second. Okay. Okay. What I'm saying is, okay, we'll go with the flow. Xj minus 1 input gate cap, xj. This is the first one, this one, and this is the xj plus xj plus 1. Okay, and this is the second gate. Correct? So this is the d tau by dxj, and I'll equate this to 0. Here what happens is, you'll get no useful insights from this. So I have done nothing. I did take this expression, I differentiated with respect to xj, and I have got only two terms, and I have said the intuitive approach, like straightforward approach, why it is only these two gates. And if I equate that to 0, let's differentiate this first. D tau by like d dou by dou xj. So this is constant. If I take this to that other side, it will be 0. So xj minus 1, it's another variable, it will be 0, and xj will give 1, and xj will give 1. Xj plus 1 is entirely different thing, it will be 0. So 2 equal to 0, like there is no meaningful, like what is this 2 equal to 0, there's nothing to do here. So what we do is, uh, we do a small manipulation to this, mathematical manipulation to this expression. From where did this expression has originated, like from where we got this expression? So let's say there is only one inverter. I have this expression, time constant kr, diffusion cap plus load cap, and I have n number of inverters. So I have added all the propagation, all the time constants of all the gates, and I got this expression, right? So we'll do some manipulation to this initial expression, so that if I differentiate this, if I differentiate this tau with respect to some inverters sizing variable, I may get some useful insights with this. We'll do this now. We'll do some manipulation to this equation, this one. So take that out. Tau is equals to, let me use another color. Tau is equals to kr min C diffusion. I'm always saying C diffusion, C diffusion. There is no contribution of source wala diffusion, so I should say drain. So C drain plus C load. This is the expression, right? So I'll do some manipulation here. I'll include gate cap. I'll tell you why. This is the gate cap, and I'll divide it so that the entire expression will be intact as is. So I have changed nothing. This will be cancelled out. It will be 1, right? So why I included this C gate, I multiplied and divide this. I'm trying to involve these capacitances. Why? We have covered a beautiful relation that if I multiply fan out of each and every stage, I'll get load cap by input gate cap of the first inverter. Like output load cap of the last inverter and the input gate cap of the first inverter. That ratio I'll get if I multiply everything. So there is something about this we can exploit so that we can get some useful insights. And one more thing, if I differentiate this, it is coming out to be just 0. There's nothing, there is no proper useful insights in that. So if I include some other variables like C gate, input gate capacitance of an inverter or any logic gate, then I might get some useful insights. Let's see. So let's multiply this C drain by C gate and C load by C gate. On outside I have some like this numerator wala y here. So here, if you recollect once again, this entire thing, C drain by C gate is nothing but gamma, which is approximately equal to 1. So I can, let's write this as gamma itself. Okay, gamma plus C load, right? C load by the gate cap. Okay, and this is armin, and this is gate cap. This is k. Correct? Clear? So, and even will there is some concept here. We will come again to this. Okay, I'll 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 definitely come to this. Now this is the delay of single inverter. Okay, but I have chain of inverters, as you can see over here. I have chain of inverters, so I need to add all this, not multiplication. So TP1, same story, same thing. Top P4, so on, Pn minus 1, Pn, right? So I'll try to I'll try to draw this again. Please bear with me. First one, second one, third one, fourth one, so on. There is some jth gates. Okay, this is load. This is the nth gate, n minus 1, and this is the jth gate, j plus 1. This is j minus 1. This is 1, 2, 3, 4. This cap, like I have sized it to some factor, thus I have some capacitances here. Here as well. This is actually not really required. Let's write it. Clear? There is the input gate cap. Okay, so this is the minimalistic one, right? So this will be 1, correct? This will be what? This is input gate cap of second inverter. Okay, so I can write this as x1. Okay, no issues. This load cap is input cap of this one. Let me write it as x2 here, like it is connected to 2, right? So this is connected to 3, this is connected to 4. Connection in the sense, not the physical wire connection. I'm telling about the inverter gate cap of fourth inverter is x4, which is acting like a load cap for the third inverter. So this is x5, and this gap is xj plus 1, sorry, xj minus 1, xj minus 1, and this will be xj, and this will be xj plus 1, and this will be xj plus 2. This is xn minus 1, xn, that is actually xn plus 1, which is cn. So now if I write the expression that we have, kr min 3c, wait, okay, this is c gate, and the expression turns out to be first gate diffusion cap, which is x2, x2, no, sorry, first gate output cap is x2, but the diffusion cap, like drain cap, is 3C, right? Uh, Actually, we are sizing all these gates by some X factors. So the unit cap is always 3C. So every capacitor within this square braces will be having 3C. So let's take that as a common and write it as 1. 1 plus x2 plus um, and I forgot one thing. Sorry, I'm really sorry. I have introduced this gamma thing, right? It's not actually drain cap. Drain cap by gate cap, which is gamma. So this is gamma, and there is no 3C here. Plus, what is that? Load cap is x2, and input gate cap is. Now I need to write this. Okay. So input gate cap is actually okay, write it as inverter. I'll tell you some factorization later. And gamma for every inverter doesn't change, because you may say that this gate is sized by x1, this gate is sized by x2, this gate is sized by x3, xn, xj. So why gamma remains same? See, drain cap over gate cap remains always equal to 1, almost. Why? In CMOS, if you see these, where is this diagram? Yeah, if you can see this, if you increase the width of gate, that in the sense you are also increasing the diffusion as well. The diffusion will be increased Horai. Width of the diffusion is also increasing. So capacitance of diffusion drain increases as much as the gate increases, right? So there is no change in gamma. Gamma is just the ratio of drain cap to the gate cap. So gamma remains same for every stage, every gate. So gamma plus second inverter's load cap is x3, input gate cap is what? X2, and gamma plus load cap is x4, input gate cap is x3, and so on for j minus 1th gate. Gamma plus xj by xj minus 1 for jth gate will be gamma plus xj plus 1 xj plus gamma plus xj plus 2 by xj plus 1, correct? And so on for n minus 1 gate, it will be gamma plus xn by xn minus 1. For nth gate, gamma plus load cap by xn. So this is the time constant expression with some manipulations in the initial equation. Okay. So gamma is there in each and every term. So if there are n gates, it turns out to be n gamma, right? So I can write it as tau is equals to n gamma k r min c gate. Gamma, I have taken it out. So 1 plus, I can say that for a gate cap output cap by input cap is nothing but fan out of that gate so I can write it as 1 plus f1 first gate plus 1 plus f2, correct, 1 plus f3, 1 plus f4, so on and so forth, 1 plus fn minus 1, 1 plus fn, correct. I can write now. So slowly you might be getting why we are doing this, didn't you? There is this beautiful relation. If I multiply each and every fan out in the chain of gates, in chain of these inverter gates, if I multiply each and every fan out of each and every gate, it turns out to be output cap by input cap of the first gate, correct? So I can write that f1 f2 f3 multiplied by each and every stage, it turns out to be CL by gate cap of the first inverter. This is load cap of the last inverter. Okay, so this is the expression. So now I need, why did we do all this? Because if I differentiate tau with some variable, I didn't get anything. Now we'll try differentiating tau. We may get some useful insights. So let me differentiate tau with some jth capacitance. Okay, so as you all know, I don't have to repeat it again, or else you have this, no? So I'll get this gate and this gate. Okay, there is some issue with one node. Okay, so maybe you can just copy this, paste it here for reference, change the color, and okay, so I have a reference. Okay, so uh, if I just write this constants and C gate, so if I differentiate this fan out, wait, okay, yeah, so if I differentiate j minus 1 gate, so xj is differentiating 1 plus fj minus 1 plus xj, actually this is xj minus 1, I'm sorry, this is xj, this is 1 plus fj, so I equate this to 0 and differentiate, like what is fj minus 1? Fj minus 1 is nothing but xj by xj minus 1. So xj by xj minus 1, 1 plus, and that 1 plus fj is xj plus 1 by xj. So if I differentiate this by xj and equate it to 0, this will be 0, this will be 0, and this will be xj minus 1 plus some constant by x d by dx. What is the expression? So x d by dx of c d by dx of x and c by x square. So you'll get xj by dou xj, which is some other variable, minus xj plus 1, so by xj by xj square equal to 0. So this is 0, so 1 by xj minus 1 minus xj plus 1 xj square. So 1 by xj minus 1 xj plus 1 xj square xj by xj minus 1 xj plus 1 by xj. So there is some useful insight. Previously we got nothing, no insightful information. Now, after manipulating the delay equation by including this input gate gap, I got this relation that this is jth gate, let's say j minus 1 gate, this is jth gate, this load cap will be xj, this will be xj minus 1, this will be xj plus 1. So what this expression is saying that this xj by xj minus 1 is nothing but fan out of this j minus 1th gate, correct? And xj plus 1, this is a bad color, xj plus 1 by xj is just the fan out of jth gate, correct? So what it implies is fan out of each and every gate is equal. Okay, each and every gate's fan out is equal. So what can we do with this? We don't know. Let's see. Each and every gate fan out is equal. Let's find out what we can do. So this is the differentiation part, right? So where is the actual equation? Okay, this is the actual equation. This one. So if you can see, all these are equal, correct? Correct. So I can write kr min gate n comma of 1 plus n f. F is electrical, sorry, isolate. rectangle. Okay, F is just the fan out. Okay, just the fan out of each and every gate is same. So I consider F as the fan out of every gate, and there are n gates, so I get NF, and I can include gamma as well. This is tau, right? So now what I got to know is ratio of output cap to input cap is same for each and every gate, right? I got some insights. Let's find out what is this exact ratio, what is this exact fan out value, or how it varies with the other parameters. So again, differentiate tau with respect to f, equate to 0. Simple. So what is f? F is each and every stage fan out, right? If I consider this, every stage is multiplied and it is equal to load cap of the output gate, like last gate, first gate input capacitance, right? So from this I can write that f power n, because f1 multiplied by f2, f3, f4 and so on, fn will be f power n. So load cap and gate cap, correct? So with this can I can consider n as, like, I can apply ln natural logarithm. This is f. This is ln of C load by C gate. So n will be ln of, let's consider this CL by CG as capital F. Capital F by ln F, small f. So this is the n value. So maybe it's a good thing that I differentiate. No, let's keep this as is. Yeah, let's keep this as is. Yeah, okay. Tau is equals to n to है and gamma k r min c k k, and I take this gamma inside because gamma is a useful factor. Like what I'm trying to say, gamma is multiplied by n, right? So let's take this inside, and f, right? You got it, right? This is n gamma. If I take this gamma inside, perfect. Okay, why did you even take this gamma outside? That doesn't make any sense. If gamma is here, then I should divide it by gamma, right? So why didn't I mention that? Sorry guys, I might have confused you. So there is no gamma here. Gamma is inside only. Okay. Sorry. Gamma is inside itself. Uh, let's say everything is divided by gamma, or you can just Put that inside, man. You get na? Comma, 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 comma. So, mm, here, if I differentiate with respect to f, mm, so this is constant r means secant. This is ln f, ln small f, comma plus f. This and I wrote it like this is 0. So sorry for the disturbance. So mm, so ln f. Okay. Ln f is constant. You can keep that as an equated to 0. It will be 0. So this is the this is the term that I have to differentiate and equate it to 0. So what is this? U by v. So u by v ln f, differentiation of comma plus f is 1. Fine. And comma plus f, differentiation of ln f is 1 by f, right? And ln f square 0, this is 0, f ln f minus comma minus f and 0. So f will be gamma plus f, correct? And if I take f to the other side, gamma by f plus 1. So to reduce, like to eliminate this natural logarithm, I'll and isolate this f. I'll introduce exponential. I'll get f. This is 1 plus gamma by f. So this is some useful insight as well. Again, I got to know the fan out of each stage to be e power 1 plus gamma by f. And it turns out that, let me be clear to the point, tau depends on what? K, it is a constant, r min, okay, usually drain cap plus load cap. I have manipulated that with the gate caps as well, right? So this is gate cap, this is gate cap. So this entire thing is gamma plus this thing is fan out. So K R min C gate tau. So delay depends on fan out. It is directly proportional. If the fan out is high, delay will be high. Correct? So here, from here, I'll pull out some useful insights. See, gamma is C drain cap by C gate cap. Usually it is almost equal to 1. I'm emphasizing this a lot. Okay. Drain cap can't be 0, right? Let's say drain cap is 0, gamma is 0. and if I put that in f expression, I'll get e, which is 2.71 something. So for gamma value at 0, it starts from 2.7. Okay, what f? Okay, I'm recapping once again. Tau depends on f. We have manipulated the delay constant with the gate cap because we get this useful insights. Previously, we didn't get any insight at all. As you can see here, we got some useful insights, we got some expression, and delay time constant depends on fan out directly. If fan out increases, delay increases. So gamma can be 0. If gamma is 0, then the fan out is 2.71. Clear? So what is this? Gamma, let's say, is 1. Okay, f will be e power 1 plus 1 by f. If you put this equation in MATLAB somewhere, and you'll get some waveform which is exponential, and at gamma equals to 1, you'll get f value as 3.6. You can even check this out. If f has to be 3.6, put f equal to 3.6. Like, this is kind of confusing, right? Put f as 3.6, you'll get this entire result as 3.6. Okay, so for gamma equals to 1, which is standard thing, like diffusion, like drain cap capacitance and gate cap capacitance ratio is 1, approximately 1. So that is the standard thing. So at that gamma 1, you'll get f as 3.6, fan out 3.6. I think some of you have guessed where I'm reaching finally. And gamma increases. If increases, gamma increases, delay also like fan out is increasing. Why? Why? Because e power 1 plus 1 by like gamma by f, right? So it is nothing but e power gamma. We can say if gamma increases, e power gamma increases. If this entire thing increases, fan out increases. Fan out is directly proportional to delay. Delay increases. So ideally, for an optimal value, we consider gamma as 1. Minimal value, optimal value, gamma as 1. But that anode comes out to be 3.6. So in order to reduce some hectic calculations, like it will be cumbersome. So we approximate this 3.6 to 4. Okay, this is FanOut 4. Why FanOut 4? That is the optimal value. Optimal value that can be obtained at gamma equals to 1 is 3.6, and we approximate it to 4. So FanOut 4. So if gamma is 1, FanOut is 4, and you have this, this is nothing but the propagation delay of inverter. That is the standard one, like it is size to 1. That delay is nothing but pi TP inverter. This, I think I have mentioned it somewhere, that I will tell about this later. That is the thing, like inverters delay. This one. Okay, so this one TP inverter is K3 Armin C. 3C is nothing but C gate. Okay. So where is this? So C gate is 3C. So TP inverter, tau is 5 TP inverter. So this is nothing but if a inverter is loaded with 4 inverter, then this delay is 5 TP inverter. Why? It's clear because input cap is CG and this input cap is CG, 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 CG. So fan out is 4 CG by CG. You'll get 4. This is the optimal value for a chain of inverters. For a chain of inverters, if you have fan out 4, you'll get the minimal delay. Okay. So in the time of optimization, we use chain of inverters, and for that chain of inverters, fan out has to be 4 to get the minimal delay. Okay. How to calculate the fan out 4 delay? Just attach 4 inverters in parallel to the load of an inverter and find out the delay. You will get the fan out 4 delay, FO4 delay. This is FO4 delay, and this is FO4 delay, right? So let me show you how actually there is a relation, right? F power n is load cap by C gate. So this is 4 power n CL C gate. So if I add log base 4, log base 4, n is log base 4 CL by C gate. So if I want minimal delay, I need to have fan out 4. If fan out is 4, then number of stages will depend on this thing. Let's say output cap is 64 and there are some cloud. There is a cloud here and there is an another inverter, first one, which is basic one. This is one unit, and we need to know number of stages here. Number of stages in the sense we include these as well, number of inverters. So it turns out to be 64 by 1 log of base 4. So log 64 base 4 is 3. So I need chain of 3 inverters. That in the sense these 3 to drive 64 unit gate caps. 1. So this is the optimization. If you want to see how it is being optimized, see tau Armin C gate. This is entirely TP inverter. TP inverter. So N comma CL by secret N CL secret. Why did it say comma? Okay. So mm, let's say there is a single inverter driving 64 units cap, 1 unit input cap. Delay will be TP inverter comma plus T4 511, correct? And I forgot this n. So TP inverter comma is 1 root of 64 65 TP inverter. So this is the single inverter delay. If I cascade and form a 3 inverter chain, we think that delay will increase. Let's see, tau chain of 3 n TP inverter gamma plus n root of CL by C gate. So tau 3 is 3 TP inverter 1 plus cube root of 64. This is 4. So 5 3 TP inverter 15 TP inverter. So CD difference, it's almost 4 times less, 4.3 times less. This is single inverter, this is chain of 3 inverters. Delay has reduced by 4.3 times. So that's the cloud magic. So that's the magic. That's the magic of this cloud. It reduces the delay rather than intuitively if we think that it increases propagation delay. But actually, the thing is, what's happening is, as I have said, each and every gate is having a fan out of F. Each and every fan out is same. F1, F2, F3 is same. So that in the sense, if you have 64, then this has to be, and we found out that fan out, sorry, 64 root log base 4, this is 1 is n, right? N will be 3 and F will be 4. So fan out is 4 for a optimal minimum delay, minimum tau minimum. Fan out has to be 4. So CL is 64 by gate cap of third inverter has to be 4. So CG3 is 64 by 4 you'll get around 16. So this is 16, and this ratio should be 4. So 16 by cg2 will be 4. Cg2 is 4. This is 4, and this ratio should be 4. It is 4, correct? And if this is f, this is f square, this is f cube. Okay, so it is kind of what do we say, this initial thing is human. Okay, human is pushing uh, a truck. Let's say he's pushing a truck, and this truck is pushing a elephant, big elephant. Okay, a big elephant. So in a way, instead of pushing the elephant directly, we are pushing the truck first, like uh, let's say this is some generator, some accelerator. This is the human. Okay, so here I have a human is pushing this, some generator, some accelerator is pushing this a truck. This truck is pushing elephant. So this human, instead of pushing elephant directly, which takes some tau equals to 65, some constant, we are pushing this accelerator, then the accelerator pushes this truck, then truck pushes this elephant. This actually reduces delay, and it's actually 5TP inverter. There is huge change in it. So here we have some terminologies as well. For that, we need to dive into complex gates. Mm, let's end this with this NAND gate. We have NAND gate like PMOS, stack of NMOS, some load, VDD. So I don't wanna say how we size this. This is 2, 2, 2, and this drain cap is 6C, and the gate cap is 4C. So if I write delay constant, time constant, kr min, diffusion cap is drain cap of NAND plus if there is a load CL, C load, and let's manipulate this. C gate of NAND, C gate of NAND. So kr min, C gate NAND, CD NAND, CG NAND, C load, CG NAND. So what do you get? You got some expression, right? Okay. Now let's say I like initially I mentioned something that if I have a inverter, there is some drain cap and there is some gate cap. So if you want to calculate the delay, you have to have RC extracted correct? So I have to extract the capacitance and resistance. So I have to extract capacitance from here and here. Resistance is this one, some mathematical calculations and all. So now again, if I want to have drain cap of NAND gate, I need to extract this gate cap here, this one, and I need to extract the input gate cap here, and R is also important. So we can do this. We can again run some simulation, some mathematical calculation, probabilistic assumptions. If I do all those, I can get the drain cap of NAND and gate cap. Okay. But if you see, if you observe carefully, inverter is having NMOS and NMOS and PMOS, and NAND is also having PMOS and NMOS only. It's not like any some XMOS or KMOS, LMOS, AMOS, BMOS. So not like that, right? These are only PMOS and NMOS. So the characteristics of the gate remain same. Only thing that changes is the sizing. Sizing changes, right? Sizing has to be taken care. So I can write C gate NAND capacitance as 4C. C is the capacitance of a PMOS or an NMOS. Okay. And if I want to generalize this, I'll come to this again. C drain NAND is 6A. Okay. Drain cap of PMOS or an NMOS is C. So 6A. Correct. So if I include those, KR min, CG NAND, and where is this? CD NAND is 6CD. We can say drain cap, we can say gate cap. Okay. 4CG plus C load CG. Let it be NAND only. Okay. So, and I'm emphasizing it once again. This is gamma approximately equal to 1. So 3 by 2 gamma plus C load by C gate NAND. C gate NAND KR min. Fine. So I can now, I have gamma. I have characterized NOT gate and I got to know what is gamma exact value, and it is actually almost equal to 1. That's fine. What if, let's say, what if I, let's say I'm doing this for all the gates, NAND, NOR, and OR, XOR, XNOR, XOR, all these has to be calculated, right? Characterized. But what if I change the technology? Let's say this is 16 nanometer. I switch to, let's say, 180 nanometers. I need to characterize not NAND, NOR, and or some mux, some adders, some half adders, full adders, something like that, multiplexer and all. I need to do again for the new technology. I have to extract R, I have to extract C. That has to be done actually. But the thing is, I need to do each and every gate right. I have to calculate the entire standard cells again if I switch to other technology. Let's do one thing. Let's describe any gate in terms of inverter. Okay, so that if I characterize inverter, I can be able to characterize every gate with these relations. We'll get some numbers. So tau k r min. So c k NAND is equal to 4c. So Cg inverter is 3c. So I can write Cg inverter by 3. Okay. Drain of NAND. C drain of inverter is 3c. So Cg inverter total. So if I include Cg inverter 4 by 3 second comma plus say load by gate NAND. We'll keep this as is. We'll come to know why it's kept like that. If I bring these two inside ratio, this will be PP inverter to gamma plus 4 by 3 C load C gate NAND. So at the end I'll get so here I present the three terminologies. So I'm emphasizing that I'll keep this CG9, CG9, CG9. Why? If you can see for an AND gate, real CG9, this is fan out, right? So this is fan out. Okay. And this is 4 by 3. So this is called as electrical effort. And this is considered as logical effort. And is considered as parasitic effort, correct? Ah, so what is parasitic? Parasitic is nothing but um, from where this karma comes from, seed drain to seed gate. These are parasites, right? For an inverter, VDD, this will be diffusion cap, which is produced by this one and this one, and we'll have this input gate cap. So we are not driving any load cap here. These are intrinsic. Okay? So this will be parasitic effect, and this is electrical effect. Fan out can also be called a fan. 4 by 3 is logical effect. Logical effort says that how much effort that has been incurred when we try to add some other logic to the CMOS structure. Let's say this is inverter topology, and if I add NAND gates in parallel and one more here, you are changing the topology, and input cap is increasing, and diffusion cap, drain cap is also increasing. So it's kind of how much effort you are putting in other than from the base level. Base level is the inverter, and how much effort are you are adding to the logic gate by a factor of inverter's effort. Yeah. So I told you about parasitic effort, logical effort, electrical effort. So this actually these parasitic and electrical effort are just numbers, constants. Electrical effort fan out changes actually. C load by C gate cap, right? C load doesn't depends on width sizing of the gate, but this depends. So fan out actually reduces if you size it by W. So that I forgot to mention. So that's the thing. You need to have W by W. That wait. One minute. So fan out is C load by C gate by W. That's it, guys. Boy.